10, Physics 1101. Chapter 10, B lecture. And this is on fluids in motion. Okay. Including the continuity equation. Okay, so what we have here, we'll be doing a couple of things here. Bernoulli's Principle, Continuity Equation. So this is section 10.8. We'll start with. I've already done the first half of the book, of the chapter I should say, and this is the second part. So, let's look at fluid, and for the most part, we'll be dealing with liquids and gases. But for this first part, we're dealing primarily with liquids, but this could also apply to a gas. And you might have this when you have a hose, all right? And you want to have it come out, you know, if you just have the open hose, the water kind of flows out at a certain rate. But if you want to have it come out faster, you either get like a nozzle to put on it, or put your thumb over it to allow only a smaller area to come out. So if you have an area 1 here of a pipe, and it shrinks down to area 2, and we have a liquid coming in, there's a certain amount of volume. This volume coming in here has to come out here. So if this is a smaller area, we think of the flow rate is the cross-sectional area, and this will be in meters squared, times the speed or velocity in meters per second. So we end up with a flow rate of volume per second. So in this case, we have A1, V1, which is the velocity here, and the velocity coming out here is V2, and that'll be equal to A2 times V2. That makes sense because whatever you have coming in has to go out unless it's leaking somewhere else. So if we're trying to do it, so this is what we call the continuity equation. So if, in this case, if A1 is greater than A2, getting smaller, then V1 is going to be less than V2, so this is going to be coming out faster. That's what we call the continuity equation. Not a whole lot to it, but I'll leave that up there as far as that's concerned. Okay. We're also going to be dealing with this in the second part, and I can get to this now, but related to this is the concept of pressure. All right. Now, if we are to measure the pressure P2 and the pressure P1 here, all right, like if we had a pressure gauge showing this, what we're actually going to find is because this is moving much faster past it, then the pressure is going to be less than it is over here. So in this case, P2 is measuring the pressure as it passes by. P1 is that case. If this is the case here, then P1 is going to be greater than P2. So the pressure here will be less than the pressure here. And it kind of makes a little bit of sense because this can go up all around it. In this case, it really almost has no time to get past, so it's going past it so fast, so there's less pressure here. So P1 would be greater than P2. assuming A1 is bigger than A2, so V1 is greater than V2, less than V2. All right, so that's also related to this continuity equation. And we're going to be dealing with this now, what we call the Bernoulli equation. So I'll leave that up here for a minute, as far as this is concerned. All right, so keep this in mind, P1 and P2. All right. So I'll move on here. And let's look at Bernoulli's equation. Make sure you get that. 2 L's. Oh, but not. And this is named after Daniel Bernoulli. And what this applies to is, let's say we have an airplane wing, which would be the best example. And there's a picture, back in the book on this. And we've shown this before. And what this is what happens if I have air going over a wing and air coming here this way. So an airplane wing will has to travel farther to go over the air to come back here. So basically it comes here, it's traveling farther to go over here. So longer path on top. If we call this V1 and this V2, then what we're going to see is the pressure is going to be different here compared to here. And this is then V1 will be greater than V2, and P2 will be, P2, this will be pressure on the wing will be greater than P1. And we can write this down as an equation as P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. Where rho is the density, this is the density of the liquid or air you're flowing through. P1 is the pressure on top. V1 is the speed of the air on the top. P2 is the pressure on the bottom. V2 is the pressure on top. So I'll leave that for a second because I want to get a little demonstration to show you how this is in action. Okay. So a couple things here. Just demonstrating Bernoulli's principle. And the first I'll do is with this concept of if the air is traveling faster here, so as a result of that, the pressure is going to be less on top than the bottom. And that's because it travels farther to get here. And this is what we call a laminar flow. An example of this is if I blow air on top of this paper, not underneath. If I do that, if I blow below, kind of pushes the bottom out. But if I actually blow on top, it actually causes it to lift up because there's the air is moving faster over the top. Okay, a better demonstration of this is with this. When I have this ping pong ball, and what I'll do is put this, get this jet going. What I do here is I have this air coming out. Now, if I put this ping pong ball on top, notice that it stays there. Even at slight angles, it stays there. And why is this? Well, if you think about it, I mean, it has to go over quite a bit. Even at this angle, finally falls off. Turn this off. And what we see here, in this case, is much like the plane wing. As the air flows up around this, it pushes it this way, and then as it bounces out, there's less air going around it, so it pushes it back in. If it comes back the other side, there's less air, and so anything, if it's in the middle, the air around it is less. So it actually, as it goes out, it gets more exposed to still air, so the pressure in the still air is greater than the air flowing past. That's Bernoulli's principle as far as that's concerned. Let's see. One last thing here. This is also the concept of curveball. On a curveball, what you want to do, and this is why they rough it up, if you do a curveball, as it spins, the air coming on one side, the air is going faster, so it's going to have less pressure. The other side is going to have greater pressure because of the what do you call the wedges where you have the threading, and that causes it to push to the other side. It's going to be more pressure where it's spinning into it than with it. So this is the concept of Bernoulli's principle as far as questions related to that is concerned. And that's the only part there. So show a picture of that here. With air flowing past. So that is chapter 10. There isn't a whole lot to it. Here's our equation. And the only other one we had was the continuity equation, A1 V1 equals A2 V2. Right? And generally referred to as before and after, or this could be top bottom. So one, either top or bottom, as far as that.